Hello, students. 6.3. We're getting to multiplication and division and also estimating with rational numbers. The estimating part is not a bad thing at all. It kind of really does help you to get an idea. I'm actually going to lead off with a bit of estimating as you start this section because when you think about three groups and you say, I want 3/4 of that, what I want you to think about is, hey, 3/4, that's definitely between a half and one. So if you kind of, in a sense, round up, the biggest, whatever this thing is, it's got to be less than 3 times 1. And it has to be bigger than half of 3, which would be 1.5 or 1.5. I guess I could also write it in mixed number form, 1.5. So again, when you come down and you do a little bit of work at thinking of it as repeated addition, you get an answer that's 2.25. At least that answer makes sense. It's between 1.5 and 3. It gives you a pretty good idea of what you're doing. So what they're going to show you as you start is just a reminder of a couple different things that we've talked about. Multiplication can be interpreted as repeated addition. Um, Technically, it's a little bit more than that, but for now, and when you're dealing with elementary school kids, it's not bad to think of it as three groups of. So 3 groups of 3/4, you could also think of as an area model. They're doing circles here, but you could also use squares or rectangles. And then just pictures. So in case you're kind of wondering, how did they get from there to here? Just take one of these pieces and fill in the gap. See what I'm saying? Take one of these pieces and fill in the gap. And that's how they got 2 full objects. And then they just have one piece right here that is remaining. Okay. Now, if you are showing this to elementary school students, it's good to have objects you can actually manipulate. If it's a physical piece of paper, it's hard to really move things around. So if you're going to do this, use either paper cutouts. You can use what's on a thicker piece of paper called cardstock. If you print it on cardstock and you just cut them out, it's pretty quick and easy to slide them around. As you get into your own classroom, you can see things like fraction strips or fraction circles. Those are all available. And if you ask, I might be able to find some in the storage room. We might have a few sets. I don't think I have enough for the whole class, but just to kind of get you on the right track. All right, well, let's jump forward. Let's see here. What else could we do? We could do a bar model. This is one that uses something more like a fraction strip, if you will. So to find 3/4 of 3, then you can think of it as 3/4 times 3. And again, this is the reverse. So they're using the commutative property and trying to demonstrate that it holds true. So at first, if you say 3 times 3/4, you might think of this as 3 groups of 3/4. If you reverse that and you say 3/4 times 3, what we're thinking of is 3/4 of 3. So what you could do is you could kind of say, I'm going to start with 3 whole objects. That's the 3. And then say, I want 3/4 of each one. So I would shade 3/4 of each one and then combine my like pieces. Now notice that's different than starting with 3/4 and then just repeating it 3 times. So that is a distinct difference between the two models there. Okay. So yeah, if you had a bar model, again, the bar model is more of a visual stack. You notice here you have the whole 1 unit listed, and this would be 1/4. And so if you wanted 3/4 of 3, you would fill 3/4, and then you'd repeat that 3 times. And that's the way we can do it. So again, at the end of the day, you do get something that hopefully kind of makes sense, that if you had 3/4 of 3 units, these are the 3 units across the top, take 3/4 of each. The end result is 3, 3, 3, which is 9/4. So my final result will be 9/4. Okay. So this is a great way if you're doing fractional pieces. times a whole number, because then you could represent the whole number as a whole unit. But if you have fractions multiplied by fractions, we need a little bit of a tweak. And that's where, honestly, I think the box or rectangular model is much better. And I'll kind of tell you why. When you start doing a problem, and in this case, they're going to give you what is 1/2 of 3/5. You could start by drawing 3/5, thinking of this block right here as your one unit. What is the whole group? WHOLE. And then what you can do is you can use your other fraction, and notice the denominators are the key. The fifths tells me I need 1, 2, 3, 4, 5 chunks. The 3/5 counts how many, and that's why we would shade those pieces. The next one, what you do is come horizontally, break it into 2 groups, and then the fraction tells you that you want one of those. So you actually end up shading 1/2 of that piece. Technically, you really would only shade 1/2 of the 3/5, but it's not bad to think of 1/2 of the whole shape and 3/5 of the whole shape, because what you really find then is, where do those intersect? And they intersect down here, where you have 3 pieces kind of double shaded out of 10 pieces total. Okay, which leads us to a really nice kind of connection. Hey, I wonder if I had 1/2 and I wanted to take that 1/2 of 3/5. It seems like I end up with 3 pieces. I end up with 10 chunks on the bottom. Is that just the same as multiplying straight across? And you got to see something really cool, I hope. And because the answer is heck yes. So that is our process. Now you'll see a school book page, and they do some good shading here with different fractions. Fractions of 12ths, fractions of sevenths and thirds, and you can start to see why the box method seems to be a pretty good technique. Now what you'll notice is the way they show it for these elementary school students. And what is this? This says grade. Okay, I feel like that's got to be a typo because it says it's grade 1, and multiplication of fractions comes a little bit later. So I have a feeling that part at the bottom is a little bit of a typo in terms of what grade level this would be seen at. But anyway, so let's take a look at the picture. What they have is they have 2 approaches to this. One is that you shade in one way with one color, and you shade in another way with a different color. Then the overlap, so what they're doing is red and blue make purple. They're saying purple, the overlap is the answer. Down here, notice they didn't have red and blue. They had red with red because maybe, like you or like your students, they only have a pencil or they only have one color. And so what you do is you shade one direction with one, you shade another direction with the other, and you look for where you have these crossed over line structures. That's what you're looking for. Okay, that would kind of be your answer as you're doing it. Let's continue. So, definition of multiplication of rational numbers. Notice A over B and C over D are rational numbers. When you multiply the rational numbers, you multiply the tops and you multiply the bottoms. That's it. So, again, big pieces though, that you have to remember, it does say these are defined as rational numbers. We've already defined rational numbers as A and B are integers. And we've already defined that B cannot be 0. So if someone says a rational number and you think 5 over 0, we have to kind of say, no, that's not possible because the denominator cannot be 0. Okay, so just keep that in mind when they're using the proper terms here. All right, let's go down and take a look at some of the properties here. So what properties do we get? Well, it's basically like multiplication of integers. So you get closure, commutativity, associativity, multiplicative identity. And when you expand to the set of rationals, we pick up an additional property. And this is the property called the multiplicative inverse property. So when you have a fraction, let's go back. Let's do integers because this is the first time we saw this property. What is the additive identity? The additive identity was the number that you add to keep the value the same. And so it had to work on both sides. And so the additive identity was 0. And then 0 came back up because we came up with an additive inverse. And the additive inverse was a number that I would add to get back to my additive identity. In this case, to add to get back to 0. So if you had 2 plus the opposite of 2, sometimes additive inverse was the slang word, was like the opposite. Okay. So all we're going to do is say, hey, let's do that same thing, but now let's do it for multiplication. So if I'm doing multiplication, multiply identity, the multiplicative identity is not 0, because you don't multiply by 0 to keep the number you started with. If I started with 3, I would multiply by 1, and I could show that that works on both sides. So 1 is considered the multiplicative identity. So keeping that in mind, when you come down, you would want to end up with 1. So you could start with any number you want, and you want to end up at the number 1. And when we think of rational numbers, you could rewrite your number as an integer as a rational number, because the piece you multiply by is always what we would know as the reciprocal. So the multiplicative inverse is slang known as the reciprocal. So again, you have to multiply to get back to 1. Now you just got to be careful with this, right? Because notice we've now flipped a number over. So the number 2/3, if I flip it over, would be 3/2. And if you think, hey, let me just multiply those, perfect. You end up with 6/6, and 6/6 is just a fancy way of saying 1. Okay, what if I did a -3/4? Okay, then I'd multiply by -4/3. That would be the reciprocal. And the reciprocal, when I multiply, negative times negative is positive. 4 times 3 is 12. 3 times 4 is 12. I get 12/12, which again is a fancy way of saying 1. But let's continue on. We know we can't have a 0 in the denominator of a rational number. So if I started with 0/5, I would have to multiply by 5/0. Now again, even if that was allowed, when you multiplied, you would get 0/0. And we learned in the past few sections, 0 divided by 0 is undefined. So this cannot happen. So this is why when you look at the definition of the multiplicative inverse, notice what it says right off the bat. It says you have to have a non-zero rational number. And that is because 0 will not have a multiplicative inverse. Every number except for 0, you're good. But 0 itself will not have a multiplicative inverse. It fails the definition of division. Phew, thankfully we pushed that in prior sections, so I don't think that's going to be really a new or strange thing. Okay. There is no multiplicative inverse of 0. If you get a mixed number, when we're talking about reciprocals, you cannot just flip over the fraction. You have to write the entire number as a single fraction, known as a rational number, in order to find the reciprocal. Okay. All right, so that's the reciprocal idea. That's the idea of a multiplicative inverse. And then what are the other properties? Well, we have the distributive property. You can distribute fractions across multiplication, and it works with multiplication over addition or subtraction, I should say. We have this is a property of inequalities, so, and a property of equality. This is exactly the same properties that we saw with integers. That is, if you multiply on both sides of an equation, you're good. Nothing changes. So if you wanted half of one side and half of another, you end up with the same thing. Okay. And let's see here. Down here, multiplication property of inequality. Well, just picture if you multiply, and we talked about this in class as well, you multiply by a positive on both sides, nothing happens. If you multiply by a negative, that's what's happening in the second one, then the sign, which used to be greater than, has to change because now it becomes less than. That is like taking the opposite. And in class, I tried to say, hey, be careful. -2 and -4 is different than 2 and 4 because we know 4 is greater than 2, but -2 is actually greater than -4. Okay, if you take the opposites, the signs have to change. Okay. And lastly, the multiplication property of 0 shouldn't be a big surprise. Anytime you multiply by 0, you get back to 0. So again, I mentioned these properties, but we've already seen all of these before. We just haven't seen them with fractions. And that's one of the techniques that you get to see as you move into algebra. If a bicycle is on sale at 3/4 of its original price, if the sale price is $330, what was the original price? And so you get to see a technique. You'll see a few ways to do this. One is algebraically, and the second approach is using what's known as a bar model. And the bar model might be helpful for some of you if you like to visualize the problems that you're trying to solve. Okay. Algebraically, though, if you had an original price and you don't know what it is, then just call it something. Let's call it P for price. And the bike is on sale 3/4 of its original price. So I don't pay the full amount. The full amount would be 1 times the purchase price. But what I'm saying is I have a discount. I don't have to pay full price. Some of you might be able to look at this and say the discount must be 1/4, or if you prefer percentages, 25%. And that means you are paying 3/4 of what you started with. Now I know 3/4, the sale price is $330. So for me to continue on, one option is to divide on both sides by 3/4. The other option is to not do that, but just to multiply by 4/3 on each side, because 4/3 times 3/4, those are multiplicative inverses. And that means I get 1 out of this. So at the end of the day, I just end up with P right here. And on the other side, I could multiply straight across, or you could also remove fractions, common pieces. And so here I see a 3 goes in and a 3 goes in, and then I have 110 times 4, so the original price would be $440. If you're using the bar approach, again, the bar approach is not a bad one. Just picture, I need to think of my sale price as being 3/4 of the original price. So over here, this whole thing is the original price. Okay, but I'm not paying that much. I'm paying 3/4 of it. That's how much I'm paying. And this 3/4 is worth $330. Okay, so that might help you understand why, when you look at it, you really have 3 pieces and they make up $330. So if you kind of say, well, what is each piece then? Well, each piece must be $110, because 110, 110, 110 gets you 330. So if each of these same size pieces is $110 each, then all you have to do to get to the original price is bring in one additional portion, which would be 110. And so that's how you can get to that same final answer, is you just add one more $110 price and boom, you're up to 440. So picture approach and a little bit more algebraic approach. Both of them are perfectly acceptable and of course completely fine. Um, yeah, let's talk about these mixed numbers. Yeah. People seem to like them over improper fractions. I do not know why. They bring more trouble than they are clearly worth. Well, let's give an example. I'll use different numbers because the book did this one here. Let's say I wanted to multiply 3.5, and I want to multiply that by 4.5, right? Okay. So if I wanted to do that, if I turn them into improper fractions, I would end up with 7/2 times 9/2. My end result would be 63/4, because again, I multiply straight across. Now, if I divide this by 4, I get almost 16. 16 times 4 would be 64. So I get 15 whole groups go in and 3 are left behind. So I could leave it as either one of these. These are equivalent. Okay, that's one way to do it. The other way to do it, if you want to not turn them into improper fractions, is to multiply them as if they were added, which is the correct way to think of these because there is an addition sign between each one of them. Then use the distributive property. 3 times 4 gives me 12. 3 times 1/2 gives me 3 halves. The next one, 4 times 1/2 is, I'll just put it as 4 halves. And then the last one is 1/2 times 1/2, which would be 1/4. So end result here would be 12 plus 1/2 plus 2 plus 1/4. Okay, so let's put all the whole pieces together. So 2, 1, and 12. So that gives me 15 plus 1/2 plus 1/4. And now if I get a common denominator, I'll fluff this a little bit because this one needs a 2 and a 2. So that becomes 2/4 plus 1/4. My final answer would be 15 3/4. So again, getting to the final answer, I feel like this section down here is just, even though that's what we did with addition and it works so much easier than creating improper fractions, it's not worth it anymore. So there's a balance. There's almost a kind of you have to kind of think about what's the most efficient way to do it. And with addition and subtraction, it's in my mind way more efficient to leave them as mixed numbers. With multiplication, I think it's way more efficient to turn them into improper fractions and go from there. Okay. Let's continue on down. And again, fundamental law of fractions and addition of fractions using a common denominator. Yeah, well, that's exactly the same thing. So basically what they're doing is saying the fundamental law of fractions says that you can rewrite things by multiplying the top and bottom by the same thing. However, you could think of it, instead of multiplying top and bottom, you could think of it as multiplying by 1. And then you just create a clever version of 1 and multiply it. And using the definition of multiplication, where we multiply across tops and bottoms, it works out really nicely. Okay. And here we go. It says dividing rational numbers, says grade 6. So you're going to see a lot of fractions in grades 4 through 6. You'll see the division usually comes up in grade 6, but don't be surprised if sometimes you'll have an activity that relates to it. Because once you understand multiplication, really division comes along for the ride. Okay. So you can read through the textbook and see a couple different approaches. This one is, if you take a look, 3 divided by 1/2. And there are a couple ways to think about this. So I'm going to show you a few ways to think about it as well with different picture models. Nothing wrong with that. So they have one here on a ruler. They have one up here. But I want you to notice what they're saying is this model, and there are 2 main models for division. One is called measurement. The other is called partition. I want to show both of those because I think they're really important when you're solving problems with students. So let's take a look. So this one here is how many halves are there in 3? So what this one ties back to is the idea of take 3 whole objects, you can use circles if you want, and take a half and say, okay, there's 1, take another half, that's 2, take another half, that's 3, take another half, that's 4, there's 5, and there's 6. And you would say, aha, there are 6 halves that make up 3, and therefore 6 is equal to 3 divided by 1/2. Okay. Now that might seem a little strange. Typically, division makes things smaller, but division only makes things smaller when you're dividing by a number that's bigger than 1. If you divide by 1 itself, 3 divided by 1, you do not get something that's bigger necessarily. You get the same thing you started with. But if you had 3 divided by 3, then you would say, well, there's only 1 available. So dividing by something bigger than 1 kind of makes, if you compare what you started with and what you end with, looks like it goes smaller. Once you divide by 1, it looks like it's equal. And when you divide by something that is smaller than what you started with, the result ends up being bigger. So again, it's all compared to 1. The number 1 is really that kind of magical piece. Okay, so what we're really thinking about here with this half idea is the idea of repeated subtraction. So if you were even doing something smaller, like 6 divided by 2, let's say, 6 divided by 2. Now, you know the answer is 3, but if you were demonstrating it and you had 6 boxes here, right? You could say, okay, I'm going to think of this as repeated subtraction. I'm going to take the number 6 and I'm going to take away 2 objects, right? And I take away 2 objects again, and I take away 2 objects again. So I'm repeatedly subtracting 2. How many times did I do it? The answer would be 3 times. So if you look at this with 3 divided by 1/2, you could say, okay, I'm going to start with 3 and I'm going to take away a half. Then I'm going to take away a half. Then I'm going to take away a half. And I just count up how many halves did I take away. That's repeated subtraction. Okay, and it's a perfectly fine model. There's nothing wrong with it. It tends to work tends to work better in some cases than others. And especially if your model doesn't match, students will have a little bit of what we call cognitive dissonance. They'll understand or try to understand the idea, but it doesn't fit with the model that they can see, and it creates some confusion. Okay. All right, so if we're going to divide, again, you could do the problem with repeated subtraction, where you start asking how many 8s can I take away? And that works out really nicely. There's nothing wrong with it. But I kind of like to see something visually. And again, every time you do circles, it just leads me to scream a little bit in my mind, because a student then asks, hey, can you do that with sevenths? And you have to try to draw sevenths with a circle. So I'm going to share a new screen and kind of give you, hopefully, a really good way to think about division with fractions. So there's 2 approaches, measurement and partition. Okay, measurement is how many, so if we had 3 divided by 1/2, we would be asking how many groups of 1/2 make up 3. Okay, so what are we doing? This is the repeated subtraction. I take a 1/2 away, I take a 1/2 away, I take a 1/2 away. So again, this is repeated subtraction. Okay. Now, here's the fun fact. When you do repeated subtraction, put a little star by this, go back to section 6.2. If you are subtracting, you need to have a common denominator. You have to. Okay, so if you're going to use this technique, you need to have a common denominator. Now, this one works out really nicely with an idea for division that you may never have seen before. So I'd like to give that to you, and then I'll come over and give the partition example. And actually, I think I'm going to jump to the next page for this one, because it is so cool. Now, think about multiplication of fractions. If I'm multiplying fractions, we just multiply the tops and multiply the bottoms. It's so cool. But I wonder about that. Could we do that with any set of fractions? Maybe what if I was going the other direction and trying to divide? So let's give an example here. Let's say that I had 9 over 20, and I wanted to divide by 3/4. Okay. Now, again, you may have known some way to do this, but if you are a student in class and your teacher just said for multiplication, you multiply straight across and it works, right? If you're doing division, wouldn't you at least think, hey, maybe I could just divide straight across, right? 9 divided by 3, that's 3. And 20 divided by 4 is 5. And you'll never guess that that is exactly the answer to 9/20ths divided by 3/4. So that is it. Yeah, you could just divide straight across. It is so amazing. Um, Now, most of the time a student will try to say, oh yeah, well, that's because it divided nicely. All right, all right. Well, let's do the one that they just gave us. 3 divided by 1/2, right? And you'd say, well, yeah, 3 divided by 1 is 3, 1 divided by 1/2 is 1/2, and now it's even more confusing. And I would say, well, maybe, but couldn't I find a common denominator, right? So 3 over 1 would be the same as 6 over 2. And so all I did is just rewrite the number 3 so it has a common denominator. And now 2 divided by 2 is 1, and 6 divided by 1 is 6. And my answer, as we saw on the previous page, is 6. I know it may seem crazy, but I'm just letting you know it works. Not only does it work, it connects right back with what students already saw. So instead of making division of fractions and some crazy thing that you have to remember something completely different, maybe it's not. Maybe it actually does work this way. All right, all right. I know some of you are like, well, what can you make up a complicated one? All right, we'll just make 2/3, and we want to divide by who knows what, right? 3/4? Who knows, right? So you look at this and you're like, aha, you can't do it now. Well, you can. Make the common denominator. So give this one a 4 on top and bottom, give this one a 3 on top and bottom, right? That's a common denominator. So the end of the day, I'm basically rewriting the problem so that I get something beautiful. 12 divided by 12 is always going to be 1. Now, the numerator would be 8 divided by 9, which I know some of you are saying, aha, it didn't work. Well, hold on. 8 divided by 9 is just 8/9. So, yeah, it actually did work just fine. Not to mention the fact that if you had something like this, once you know the common denominator is going to work, you almost don't need the common denominator because you know it will be 12 divided by 12, which is always going to be kind of like dividing by 1, and division by 1 never changes the value. So yeah, it's actually pretty convenient. And so if I was doing something like this, I could rewrite this as 3/7 divided by, I don't know, I'll make up another one, right? 5/8. I don't know. I'm making up numbers now. So this one looks kind of crazy, but again, if I wanted to get a common denominator, I know I could, because I could just make this one have an 8, that one have a 7. So this one needs an 8 and that one needs a 7. And the denominators are going to be 56 divided by 56. So they're going to go away. It's going to be 1. And I'm going to be left with 8 times 3, which is 24, divided by 7 times 5, which is 35. And there's my final answer. Here comes the fun fact. You want to check it. I know you do. So go right ahead. 24 over 35. If I multiply that by 5 over 8, do I get back to 3 over 7? Let's check it out. First off, 5 and 35 share a common factor of 7, and 8 goes into 24 3 times. So I remove common factors using the fundamental law of fractions, and my end result turns out to be 3/7, which is exactly what I started with. So it does work. It does check. So don't think that fraction division is anything different than just kind of dividing straight across. It always works. Now, some of you will say, hey, but my teacher showed me a different way. Hey, knock yourself out. As long as you can understand where that came from, then I think you're good. It's very rare to have someone in this class really understand why you multiply by the reciprocal. They know that they do it. right? And I'm going to tell you, when I came out of elementary school, went into middle school, high school, I would multiply by the reciprocal, but I really had no idea why. I really had absolutely no idea why. So there's a couple different ways that we can think about it. But again, I want to show you this because I think it's relevant that you understand that there are different ways to do division of fractions. Okay. So let's take a look here. Let's do one that's a little bit more complicated. We'll show how to maybe do a picture of it. And if we need to, we can do more in class as well, but this will at least give you something you can verify. So let's take and we'll do some crazy looking ones. Maybe we'll do some with mixed numbers so it just looks a little bit more complicated. Let's try to find what is 5 1/4 divided by 2 1/3. Okay. So 5 1/4, but I'm going to divide it up by groups of 2 1/3. Okay. So again, if you wanted to, you could draw 5 1/4. So I'm going to draw those here. So watch this. Every piece turns into quarters, and I'm just going to draw 5 of them. And then I'll draw one extra piece. So 1, 2, 3, 4. Here's 5. And I didn't have to worry about circles. This could have been sevenths. Whoop-de-doo. I just draw the pictures here, okay? All right. So there, this actually turns out to be 6. What I'm going to do is I'm going to come down here and make sure it's very clear that I'm not using those pieces at the end. So what I'm really starting with is 5 1/4. Okay. Now notice I'm dividing them up into this group. So I need to come over here and take away 2 1/3. And I need to do that as many times as possible. Okay. The problem is these pieces are quarter sizes, not thirds. So what I could do is make each one of these chunks, split it into thirds as well. So watch this. I'm going to go horizontally now and cut them into thirds horizontally. Okay. So yes, in my picture, to be perfectly honest, I maybe didn't even need the vertical lines to start with. I'm just putting them in there so you can see that it'll always be kind of the same values. Okay. So each time what I'm really doing, and this may seem a little strange, but I'm really turning all of these into common denominators. This became 5 3/12. Okay, and you can see here 5 3/12. And I'm dividing up into groups that are 2 4/12 because that's what 1/3 becomes. So by doing this little picture here, which is really then finding quarters of thirds, if you think about it that way, that's what I ended up with. So now what I'm going to do is I'm going to start making groups that are this big. So I need to take 2 whole objects and I'm going to shade them with a different color so you can kind of see it. First one, I'm going to shade with a bright pink. So I need 2 whole objects. There's 1 whole object. There's 2 whole objects. And now I need 4/12. Okay, so I need 1, 2, 3, 4. Okay, so that means right here, this is one group of 2 1/3. Next up, I'll choose, what should I choose next? Green? Okay, I'll choose green. I'm going to make another group of 2 1/3. So I'm going to take 2 whole objects. There's 1 whole object. Here's another whole object. That's 2, but I need 2 4/12. So I come back up here and I find 1, 2, 3, 4. Okay, so that green part right there is my second group of 2 1/3. But now I have some pieces left over. And this is where I think if there is confusion, where it kind of comes in. I have 1, 2, 3, 4. So there's 4 little pieces plus 1, 2, 3 plus 3 more pieces. So I have 7 pieces left over. And they really are 7/12, but that would be a 12th of a whole object. I'm trying to make groups of 2 1/3. So when you look at the number of pieces it takes to make a 2 1/3, which is the same as 2 4/12, you could think of saying this would be the same as the two objects requires 24 of the little pieces, and I need an additional 4 pieces. So the grand total is 28 twelfths. Okay. So 28 twelfths is what's needed. Well, I don't have 28 pieces. I only have 7 pieces. So my remaining answer would be I can make 2 whole groups, and I have 7 pieces remaining out of the 28 pieces that are needed to make one whole group of 2 1/3. And now sometimes you can simplify this. Sometimes you can. So at the end of the day, I end up with 2 1/4. Now, if you wanted to check yourself, you could multiply 2 1/4, multiply that by 2 1/3. Your answer should be 5 1/4. If you get these into improper fractions, that's 9/4 times 7/3. And let's see here. That does simplify a little bit because 3 goes into 9 3 times. This becomes 21/4, which is 5 1/4. So it works out perfectly. So again, this approach is a common denominator approach. It's repeatedly subtracting chunks to get to the total. Okay. So that's the idea for this one. And I did use mixed numbers on purpose. Okay. On purpose. Let's see here. Maybe I should do one more of those. For this one, I won't do mixed numbers. I'll use I'll just use smaller fractions. That's fine. So let's do 13 15ths divided by, I have no idea, right? Here, let's do, what do you want to do? Like a third? I don't know, right? 1/3? All right. First off, I should have chosen smaller numbers because drawing this is going to be a real pain, but it's so much easier with boxes than it is with anything else. So first off, think of this being my one whole object. And I need to make 15ths because that's how much I have. And then I'm going to start taking away thirds. Okay. So I need to make 15ths, 13 15ths. Okay. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and that should be 15 pieces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 pieces. Okay, there we go. Perfect. 15 pieces, and I only have 13 of them, so I need to make sure that these last two, I'm just going to put a little mark on here and say those are not part of it. Okay, so I just need 13 15ths. Now I need to divide it up into groups of 1/3. Okay, so that does seem a little strange, and there are a couple ways that you could go about doing it. But if you found a common denominator, and in this case, multiply by 5 and 5, you could help yourself see what kind of repeated subtraction you're doing here. This is 13 15ths. I'm now dividing by 5 15ths. So what I'm doing is I'm subtracting 5 pieces at a time. And while you may not see it, you've really turned this problem into 13 divided by 5. Okay, you have 13 pieces. You're cutting them up into groups of 5. That's really what's happening. So if you need to change colors, so I want to take 5 of these. There's 1, 2, 3, 4, 5. Okay, right here, that's one whole group. Let's do the next one. I'll do green. 1, 2, 3, 4, 5. Okay, here's the next one. That's the second group. Now, what remains? Let me do like a purple. Okay, 1, 2, 3. And you say, I've got 3 pieces left. And even though each one of those pieces is 15ths, remember, you're not counting 15ths anymore. You're counting these chunks right here. And it takes you 5 pieces to make one of your thirds. So what you're left with is you're left with 2 whole times it happened. And you have 3 pieces left out of the 5 that you are actually needing to make one whole chunk. So the answer here, 13/15 divided by 1/3 is 2 3/5. Or if you prefer, you could write this as 13/5. And huge hint, what an amazing connection to dividing straight across, right? Because 15 divided by 15 is 1, and 13 divided by 5 is 13/5, which is the exact answer to this problem. So here's what I want to tell you. If you are doing a measurement problem, so you say, how many groups of 1/2 does it take? How many half cup measuring cups do I need to make 3 cups of flour? How many times do I need to fill that up, right? When you say that, your model that you're showing a student needs to match. You need to be able to show that you're distributing. If you are not doing that and you are inverting and multiplying, it will not make any sense with the problem. So that's why make sure your model that you're demonstrating matches the problem that you are actually solving. Okay, so that is the common denominator, also known as repeated subtraction, also known as measurement. All of that's good. So now I said I'll do the other one, which is partition. Okay, let's go back to whole numbers. If we had 12 divided by 4, and we said we know the answer is 3, we could answer this question in a couple different ways. I have 12 cookies and give 4 to each student. How many students can I give cookies to? How many? So take a look at this. Think about what you're doing, right? In this problem, I have a certain amount. I take 4 of them and I give 4 to a student. I give 4 to the next student. That is repeatedly subtracting. This question here is measurement. That's the model that you'd want to use. If you go the other direction and instead you say, I have 12 cookies and 4 groups, how many for each group? So another way to think of this is how much in one group. They're all going to be equally sized. Everybody's group's going to get the same amount. This is a very different approach. This one, you would have your 12 cookies. They will be represented by little dots. And you would say, I have 4 groups. So if you were doing this problem, you'd come and say, okay, I'll take one of the cookies and put it here. I'll take another cookie and I'll put it here. I'll take another cookie, put it here. I'll take another cookie and I'll put it here. See what you've done? You've kind of distributed it to each groups. Even though you did subtract 4, you didn't subtract a group of 4. You subtracted one at a time, one for each of the groups. Repeating that means you would add one additional cookie to each group. Doing it one more time, and you could see you would put one more cookie in each group. The question, how much is in one group, would be 3. Okay. This is the partitioning model. You're breaking it into parts, okay? Breaking it into groups. And so this model is very different when you try to explain how do you do something, because you cannot use the repeated subtraction approach when you're doing this problem because it doesn't make sense. And it really is more of a struggle when you have problems you may not see the answer to. Let's jump down and try one of these now with the partition model. Okay, 3 divided by 1/2. Okay, now in this case, we already know the answer, right? But what we're saying is, let's turn it into words. I have 3 cookies, and that's enough for half of a group. Okay, how much for one group? Okay, so now you know you have half of a group. So what you could do is you could draw out, here's one whole group. That's one whole group. But I don't have enough for one whole group. I have enough for half of the group. That's what it tells you. And half of the group is 3 cookies. So to make one whole group, you can almost look down here and say, aha, well, I just need another half, which is another 3 cookies. So my end result, yes, turns out to be 6. So 6 cookies in one group. But that picture is very, very different. You notice I didn't break 3 into little halves and start pulling halves and see how many halves I have. That is not the same thing. This is a very different approach. So notice this time, instead of drawing the 3 and then starting to do repeated subtraction, I actually draw one group and I look at how much I have of that group. Okay. Shall we try it again? Let's try it again. Okay. Let's, instead of 3, let's do a fraction then. Okay. I like that. I like that. Let's do a fraction. Okay. So here we go. So let's say 3/4 divided by 1/2 equals I don't know what. So if you want to put this into words with partition, it means you have half of what you need. Okay, so if you want to picture this kind of more as maybe instead of cookies, let's think that you're making cookies. So you have 3/4 cup of flour, and someone says, hey, that is half of a batch, right? So that's how much you would need to do half of a batch. My question to you is, how much for a full batch, for one batch? So what you would do is, again, think of your answer. I want one full batch. Got it. I want one full batch. Do I have a full batch right now? No, I have half of a batch. Okay, well, how much is that half of a batch? That half of a batch would be 3/4 of a cup. So to make a full batch, right, I would need another 3/4 of a cup. Total, when you add these together to make a full batch, would be 6/4. Or if you want to break it down, this would be 1 2/4 or 1 1/2. So 1 1/2 cups of flour is what I would need. Very, very different pictures for measurement and partition. If you want, because I know some of you are like, what would measurement look like? Measurement, I would start by drawing 3/4. I would say, here's 3/4, and I want to try to make things that are 1/2. So 1/2, which is the same as 2/4, means I would start counting up how many times can I make groups like this. And I would count up and say, aha, that happened one whole time because I got 2 of the fourths. But because 3/4 didn't fill the whole space, I don't have enough for my next component. So I have to say, okay, this next component right here is not a full group. You see, a full group took 2 pieces, so this right here is half of what I'm looking for. So my final answer here would be 1 1/2, which again is exactly the same thing I have on the left-hand side. All right. So there it is. There it is. Now you may not see it, but this partition model is the invert and multiply approach. It really is. It's built in here. So let's take a look at what happened. I said I had I said I had 1/2. I wrote that here. So I wrote down the entire number, 3/4, right below it. That right there is dividing by 1 because I wrote the whole number down. Then you'll notice I needed 2 of these to match up perfectly, which is multiply by 2. So I'm going to put down kind of what I did in steps. I took 3/4. I used it as the one portion that I had. So I divided by 1. Then I multiplied by 2. And again, if you divide by 1 and then multiply by 2, that's the same thing as multiplying by 2 over 1, because you divide by the 1 and multiply by the 2. So at the end of the day, 3/4 divided by 1/2 is the same as 3/4 times 2 over 1, and this model demonstrates it. Let's do one where the fractions look a little bit different, and I need to do one that doesn't have a 1 on top to demonstrate what happens in that case. Okay. So next partition example. Okay, so let's do, I don't know, we'll make up some numbers here. All right, 2/3 divided by 3/4. You want to think of a realistic explanation for this. When would this come up? I have 2/3 cup of sugar. Okay, that's not enough for a whole batch. That's enough for 3/4 of a batch. Question is, how much for one whole batch? Question mark. All right, so this one, what am I going to start with? I'm going to draw one whole batch. There's one whole batch. And now the question for you, do you have one whole batch right now? And unfortunately, no. I have 3/4 of a batch. So I'm going to mark down, there's 3/4. That's what I have right now. So I'm crossing this one off because I don't have it right now. I have 3/4. And notice how much that is. Okay, how much is that right now? That is 2/3 of a cup of sugar, but it fills up these 3 pieces. So what I need to do first, what would be really helpful for me, at the end of the day, I need one whole batch, which would be 4 of these chunks. So at the end of the day, I need to get down and say how much is in just one of these little pieces. And since there are 3 identical pieces, I need to basically take 1/3 of that amount. So what I'm going to do is I'm going to do 2/3 times 1/3, which gives me 2/9. Okay, now why is that so important? Because now I know how much is in each one of these boxes. I know there's 2/9 in each of the boxes. Okay, I could write 2/9, 2/9, 2/9, 2/9, and you could just add them repeatedly. But I want you to notice, how many boxes are there to make one whole batch? And I can see 1, 2, 3, 4 whole boxes. So I take my 2/9 and I say, just give me 4 of those. And I end with 8/9. So my final answer is 8/9. So one whole batch would be 8/9 cup of sugar. Okay. Perfect. Now, if you want to kind of say, well, how does that connect? Well, think about it here. If I was going to use the old tried and true invert and multiply, what I would do is I would rewrite this as 2/3 times 4 over 3. Now, no matter which way you go about doing it, you're going to have to do them in order one way or another. So this is the same thing as 2/3 times 1/3 times 4 over 1. So all I'm doing is breaking this up to show in the model, all I did first is I found 1/3 of my amount, and that's what I needed here. And then I knew that I needed 4 pieces to make one whole batch, and that's why I multiplied by 4. Okay, there you are. So that's why invert and multiply works, because all you're doing is breaking down to see how much is in one piece, one little piece, and then how many pieces do I need to make a batch, right? And so this is 2/3 of a cup. This is 2/9 of a cup. You multiply, you get 8/9 of a cup. Okay. Scott, what would that look like with the measurement model? Awesome. What a great question. Measurement with the same problem. So side by each, 2/3 divided by 3/4. What is the measurement problem? It is repeated subtraction. So I would draw 2/3 of one whole object. Let's see, how do I want to do this? Maybe I'll do it this way. I'll do it horizontally. Okay. So you could say to yourself, aha, That's what I have. I have 2/3. So I'm going to use black and kind of say, not this piece. Don't include that. I only have 2/3 of my whole object. Okay. So now I say I need 3/4. I need to count up 3/4. Well, in order to do that, I better have pieces that are quarters. So I can break this as well into quarters. I'll do half, half, and half. So now I've broken the whole shape into quarters. Okay. But what that did is it changed the 2/3. The 2/3 now, if you think about it, looks like 1, 2, 3, 4, 5, 6, 7, 8/12, because that's really what it represents, 8/12. And I'm divvying it up amongst 3/4. 3/4 would be 9/12. So again, I need you to think you're trying to fill up a shape that has 9 little pieces. And as you do that, you are counting 1, 2, 3, 4, 5, 6, 7, 8. You did not have enough to fill the 9. You had only 8. You had 8 pieces out of the 9 that you needed. So your final answer would be 8/9. Okay. So again, notice numerically, they will both end with the same number. However, the numbers are very different. Okay. And it's tempting to say that the answer here is it doesn't go in at all, 0, and you're left with 8/12. Technically, you are left with 8/12. But because we're making groups of 9/12, you have 8/9 of the 3/4 you want. 8/12 would reference the entire whole unit. And if you're even slightly confused by that piece, looking at those and saying, that's 8/12, it's supposed to be 8/9, you can imagine the first time a student sees fractions, how they might feel if you just say invert and multiply. All right, so I'm going to leave this as it is and go back to the textbook. Very cool. So yes, does the textbook have many ways of doing this? I'm sure that they do. So let's take a look here. Division of rational numbers. Then a divided by b, a over b divided by c over d equals e over f, if and only if e over f is the unique rational number that you can multiply to get back to a over b. All right, so now what's an algorithm for division? So an algorithm for division, they have taken an algebraic approach. Now again, most of your students will not have seen this. So while it may work for you if you've seen algebra, you're probably going to be realizing my students are going to struggle with this. Okay. What did they do? They turned the first division problem into a multiplication problem. Now it's a multiplication problem that they have to undo. So they multiplied by the reciprocal on both sides so that they could get x by itself. Again, it illustrates the invert and multiply method, but it does not show how this repeated subtraction one works, even though most American teachers use the repeated subtraction model, or at least when they give an example of a problem, it's a repeated subtraction model. So again, here's kind of the approach. Yeah, this is almost exactly the same approach. To me, I personally think it's better. If this is me personally, so take it for whatever you want, is getting the common denominator. And that common denominator so you can divide straight across. I don't believe that you ever need to kind of start by introducing the reciprocal. So if I was doing this with children, I would say, let me divide C over D. And I'd say, I want to floff these to get the same. So I get BD and BD. So D on top here, B on top there. And as I divide, I could divide straight across. If you divide straight across, BD divided by BD is the number 1. Up here on top, you get AD divided by BC. And that, when you divide something by 1, you end up right here. And I want you to notice AD over BC is exactly the result they end up with. So again, totally up to you which one you choose to do. But in talking, so my dad was a teacher for about 37 years, and he taught elementary and middle school in Washington State. And I remember he used to always sing songs with his students. And one of the songs for division of fractions was, when you're dividing fractions, don't ask why, you just invert and multiply. And he came and watched me teach this exact class at the college level. He just came because he was visiting me one day, and I said, "Yeah, sure, come on by." So he watched me teaching this, and then he said, "I get it. It actually is important that people know why." And I said, "Yeah, Dad, it really is important." Um, yeah. And to be honest, that whole dividing straight across piece was one of the questions at my interview here at MiraCosta more than 12 years ago. And I remember them asking us to come up, what's your favorite theorem in mathematics? And I gave them something like this, that if you divide straight across, the multiplying straight across, it gets you the exact same answer. And I showed them how it is super cool that you could actually do all these division problems and it all models. And who knows, ended up getting the job. So I think the biggest piece for students in this section, and I'm not going to go through each example, is really just understanding these key ideas, that if you have a word problem and it says go do something, if it's a repeated subtraction word problem, you should do a model that matches repeated subtraction for your student. If the problem is not repeated subtraction, what if it's the partition model? Then you should do a partition model. Don't try to just always use repeated subtraction. I think that's when I was doing professional development for future teachers and actual teachers in Oregon, that was where they would butt heads. They're like, but this is how you do it. And they would basically recreate the problem as a repeated subtraction, but they were struggling with how do they do it the other way. So I want to make sure you know it so that you can feel comfortable with that no matter what. Okay. Estimating. So there are times where you may have to do things to find the exact value. And so up here, this is computing things mentally. So if you're computing things mentally, it's almost easier sometimes to be thinking about, especially with mixed numbers, rewrite it as 5 plus 1/6, and then you could actually just distribute in. Oh, that's so much quicker. But again, totally up to you. If you did it, so they mention it this way. I got to tell you, sometimes I'll do 5 and 1/6, and I'll multiply by 12, and I will change this to 31/6 right away. But then think about multiplying with fundamental of fractions, and it comes out to 62 pretty quickly. So one group of 6 out of here, 2 groups of 6 at the top, so I can remove a factor of 6, and then I just multiply 31 times 2. Depends on which one kind of works better for you. So I usually, their approach that they show here is to multiply and then kind of do the simplifying. My personal approach is I always, I divide first because it makes the number smaller. Okay, let me show an example of that with 4/5 times 20. So 4/5 times 20. You can do this problem by multiplying straight across and getting 80 over 5 and then dividing 5 into 80. Okay, and I'm going to leave that there for a moment because you're welcome to do that mentally. Or you could do the approach that I'm kind of promoting here, which is divide first. 5 goes into 20 4 times. It is a lot easier for me to look at this and say 4 times 4 is 16, 1 times 1 is 1, and be done with the problem by making numbers smaller first and then multiplying them if I need to. If I multiply first 80 and I'm dividing it by 5, now I really have to think. I have to be like, how many times does 5 go into 80? I have to do a little bit more work because the number is larger. So keep that in mind. If you're mentally calculating things, try to make the numbers easier to start off with. If you're estimating, think about how you can kind of say, hey, what am I close to? And again, we're trying to get close to an answer. We may not get the exact answer, but 24 and 5/7, that's pretty close to 24. And 4 and 1/8 is pretty close to 4. So I would probably ballpark this one pretty quickly as about 6. Okay. Yeah, that's probably been my best guess. If you were, rounding one up, if you're rounding both of them up, you're rounding the 4 and 1/8 a decent amount, and the divisor is where you tend to have your error. So if you were to do this, you would say, okay, so 25, if I rounded this up, and I'd say divided by 5. And again, the answer is pretty close, but 6 actually turns out to be quite quite a bit better of an answer, um, because I changed the divisor by the least amount possible. If you change it by more, kind of bringing it all the way up to 5, you've almost made it, if you look at it, 25% bigger instead of uh, a tiny fraction smaller. So just keep that in mind. And again, if you wanted to check yourself, you could come over here and say, well, what is 6 times 4 and 1/8? And just do the distributive property. That becomes 24 and 6/8, which would be 24 and 3/4. Well, 24 and 3/4 is really close to 24 and 5/7, like really close. So to me, that's a really, really good estimate. How close? I don't know. You could divide, you want to put it in decimal form. So 3/4 would be about 0.75, and 5/7. Let's see here. 1, 4, 2, 8, 5, 7. So that's a little bit over a half, but a little bit of that. So it is 0.714285 dot 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 dot. So you you're almost right on. So one of them is 24.7124. The other one is 24.75. I mean, you pretty much nailed it here. But if you were to multiply by 4 or by 5, like this other estimate here, then you'd have 5 times 4 and 1/8, which if you distribute becomes 20 and 5/8. I mean, you're not even close to 24 and 5/7. You're off by 4, right? And this other estimate, by keeping the divisor as close to what you want as possible, it really does restrict the amount of error you have. So keep that in mind. And let's see here, extending the notation of exponents. Nothing wrong with exponents. Exponents can be used with positive or negative. And a negative exponent simply means you are, think of it, dividing. So if you had 10 squared, you can think of that as multiplying by 10 2 times, which gives you 100. But if you think of 10 to the minus 2, then instead of think of multiplying, think of dividing by 10 2 times. And so you end up with 1 over 100. And that's really what exponents are. So a negative exponent is just fine. You can think of it, almost a negative exponent, as the reciprocal. Okay. So you could do that too. How would you do that? Well, you could come down here and say that's the same thing as 10 squared raised to the negative 1. And 10 squared is 100. And then the negative 1 power says, hey, I don't want to multiply by this. I want to divide. So think of it as the reciprocal, 1 over 100. Totally fine. And they give you this beautiful little piece right over here. And that's not a bad one. I think you will see these exponents again as we continue on through. Exponents work just fine. If you're multiplying the same base, we add. If we're dividing, we subtract. Nothing here should be really shocking. These are all properties we've seen before. If I'm raising it to a power, then I multiply. And here's the first few where we get something that looks a little bit different, because now we have a rational number and we have a particular integer. So for example, if I had 2/3 and I want to raise it to the 4th power, that's the same thing. Picture this as 2/3 times 2/3 times 2/3 times 2/3. Perfect. And we know how to multiply fractions now. So this becomes 2 times 2 times 2 times 2, which is 2 to the 4th. And 3 times 3 times 3 times 3 on the bottom, which is 3 to the 4th. And what you can kind of see is, hey, wait a minute. Maybe I don't need this middle step if I understand that it's just going to end up 2 to the 4th and 3 to the 4th. Okay. And likewise, if I have a negative exponent, right? If it was 2/3 to the negative 4th power. Well, what's great about this, remember the negative, you can think of it as, I want to divide by this 4 times. Well, if you divide by something 4 times, it's the same as multiplying by the reciprocal 4 times. So you get this beautiful property that you can use anytime you want. And I really enjoy these. So I think those are not too bad in terms of properties of exponents. Do they do more? Kind of. We saw this property before, and they kind of just put all the properties together here. I don't know why they called it theorem 6.19 because they already had all of these in different theorems, but basically they combined all of them together into one box. So this is kind of where you can look and see, here's all the properties of exponents that we know going forward. All right. Yeah, they have a few with solutions. Perform the following computations. Express your answer without negative exponents. If it does say without negative exponents, just put it in the denominator. So if you get a 2 to the minus 1, just rewrite it as a 2 to the positive 1 in the denominator. That'd be my recommendation. And I think, hey, boom, we are into the homework assessment for this one. So big pieces that I hope you walk away with. You've got to know when you're creating word problems, right? Here's word problems. You need to know what type am I dealing with, partition or measurement. And so take your time, go through a few of these, do as many word problems as you can. I'm not going to lie. And on the test, I can promise you there's going to be a question that says something about partition and measurement, and you will have to create your own questions and then you'll have to answer them. So that'll be what's coming up for this exam. If you have questions on this, please bring them back to class. I'll do a quick homework video and something else on the MCs. So, all right, off you go.